performances. And if you like just consider an atom, we can consider an atom as an ion in the core and the electrons on the valence bands. But this approach takes a lot of time to compute, and instead of we need a different perspective, and this perspective calls the DFT. So for the one who likes the equations, we can just write a Schrödinger equations for an ionic system. The big R's are the ionic position, and the small R's are for the electronic position. So in this case, the first two terms indicate the kinetic energies of ions and electrons, and the potential term contains the nuclear interactions, electron-electron interactions, and the Coulomb interactions. So we have a like huge potential term which consists all of the interaction of the electrons. But this makes like a bit something big to solve, so we need a different approach. So we apply Born-Oppenheimer approximation in this case. So in this case, we take the mass of ions much larger than the mass of electrons. So this gives us a stationary solution of the system, and hence we can just simplify our Hamiltonian a bit more by neglecting the ionic terms in the kinetic energy. And after we are reducing our Hamiltonian, then we need something more to solve this problem actually, because like this is still something big to solve. We have a potential and there are a lot of terms in this potential. So how can we simplify it? So there's a term called Hohenberg-Korn theorem. In this, there are two terms actually, and the first theorem states that there's a unique potential V having an NR such as the ground state charge density. So which means if we have a potential for the system, we can simulate this potential uniquely by using a ground state charge density. So in this case, instead of potential, we're just going to use the charge density, or this like are going to be our main approach. It's going to be charge density rather than the potential itself. And the other Hohenberg term says that energy is minimized for the ground state charge density. So in this case, since like if you have a quantum system, our ground state energy is going to be the minimized energy, and hence if this charge density minimizes our energy, then it's our ground state charge density, and it gives the ground state result. So by using these two theorems, we can basically start what we want to do. So what we want to do is actually writing the Kohn-Sham equations, which are the equations in the single electron basis. So in this case, instead of like the interaction term over the all electrons, we just have electronic wave function. This wave function are in the valence electron bands. So which means that we have some nuclear core. The core consists of some electrons and protons. And also we have valence electrons, which are on the shell of the atom. So we only consider the individual contribution of this each electron interacted with the potential functional. So in this case, our potentials are the Hartree potential for the nuclear interaction and the exchange potential for the electron interactions, basically. In this case, we don't include strong electronic correlations. These are like more like the weakly interactions, but we can add the strong correlations by using some other approaches too. So in DFT is basically a software-based package. So like we cannot calculate everything by hand. We need some softwares, and these are like very well-known softwares in the area. And for the software of choice, I use Quantum Espresso because Quantum Espresso is open source, versatile, and community-based. In Quantum Espresso, we can calculate a lot of physical quantities. And also there are some other software packages which are built onto Quantum Espresso, which allows us to calculate physical quantities further than its capabilities, actually. So let's briefly discuss something about Quantum Espresso. How does it work? So it's actually work with something called self-constant field or self-constant cycle. So at the beginning, we give a nuclear potential. In this case, it becomes our pseudo potential. And after we give like we just give the Schrödinger equation the information of atom and atomic densities. And by using our first initial particle density gas, it calculates the potential for Hartree and exchange correlation to find the effective potential for the system, and then calculates the ground state energy for the given system, for the given Hamiltonian. And by using this energy, we can calculate the charge density of the system. So in this case, if our initial guess is overlapped with the calculated charge density of the system, then we are good to go. But if not, our initial guess doesn't match with the final result in the charge density, then we mix these two results and make a further step in our calculations until like we put some cutoff, until we reach this cutoff in the difference. The iteration continues actually. Yeah, this is like how the software works. Actually, like there are many different softwares, but most of the time using this self-constant approach. But the software is mostly differs by their like pseudo potentials more instead of like this cycle. And like if you want to see an example file for the basic system, so we can I choose actually like hydrogen for an example. I choose the hydrogen molecule. In this case, we're gonna make a self-constant field calculation for the hydrogen. And in this case, we need to like indicate some parameters. First of the parameters is a cell dimension. So we are basically putting these hydrogen atoms in a box, and this gives the size of the box in Armstrong. Number of the atoms is NAT. We have 2 atoms in the box and 1 type of atom, which is the hydrogen. And we need to put a wave function cutoff. In this case, the wave function cutoff allows us to, instead of like writing the whole electrodes in the system, we just simulate a system with a pseudo potential. And until a certain point, the pseudo potential doesn't match with the real one, but after some cutoff, this starts to match. So we need to indicate our match, like at which point it starts to match with the real potential. And the other thing is electron convergence. So this is like the previous thing that I mentioned. It is the convergence of the system to a certain degree, actually. If you want like a systems that approach the real more, then we need to increase our convergence threshold. And it takes our calculation time much longer, but we can get a more correct results actually by using it. And also we have some other dynamics. It's called the ion dynamics. This helps us to find an optimization algorithm for the physical system. So we are calculating minimize ground state. So this is actually the minimization algorithm for this given system. And the other things are atomic species. This is the hydrogen, and we need to give the mass of hydrogen. And there's also something called pseudo potential, this H.Pb term. Well, this is like this contains the information of the atom in it, so we can start the calculations by using an initial guess. And in this calculation, I just put a hydrogen atom with a like 1.1 Armstrong apart from each other, and I'm calculating the energy for the system. So the thing on the right is just a manual of the quantum espresso. In quantum espresso, we can do a lot of calculations like self-constant, non-self-constant, band calculations, or relaxation calculations, and even we can do molecular dynamics in the system. So there's like there's a like huge manual that one need to do, that one needs to read before like start any calculations actually. So let's talk about the shape of the output file. So first we have our Bravais lattice. In this case, Bravais lattice 1 means it's going to be like free lattice, because in the previous slide we indicated that the lattice coordinates is like a free lattice with a cell parameter 20, and like the free lattice means it's just a box with 20 sides in each, 20 Armstrong each side. Okay, this is our lattice parameter, and then the unit cell volume. So since we have a cube, then we just multiply this lattice parameter, and then we get our volume. And the other thing is number of atoms in the cell. Like this is actually like the output file, and the output file is just a better version of the input file, and it's like says us what we are measuring the computer. So in this case, we have number of electrons 2, number of quantum states 1. So this is like the properties of the given system. And also one good side of this quantum espresso software, it can calculate the symmetries of the lattice. So in this case, if we give like 2 hydrogen atoms, like in a hydrogen molecule, we have 8 symmetry operations, but we don't have any inversion symmetry. So this is like something nice. And also the self-constant calculations are like consistent iteration cycle. So in this case, we can select iteration 1, 2, and so forth. So each calculation has a total energy and accuracy. So each calculation takes some time. It calculates the value. If it is within our accuracy range, it stops. But if not in the range, then it's continue with another iteration. And it's also not unusual to see like a lot of iteration has been done, but the conversion hasn't been reached yet. So this is like a numerical problem. So in this case, we can maybe change our kinetic energy cutoff or charge density cutoff for the system to achieve better results. But in this case, we need to spend more time on the calculations. I just gave a basic example of the hydrogen molecule, but I'm actually working on a more complex system. It's called niobium diselenide. So this is like there are a little bit more terms in the actual research input file. So if I want to discuss this file, we have like the total energy conversion threshold and force conversion threshold. So in this case, we are like putting the atoms in the system, but the atoms are attracting or repulsing each other with a force. So this force can be like this, we need the equilibrium position in the system, so the forces should be 0. But since we are doing numerical calculations, the force cannot be 0, but it should be like a numerical value or something below a certain threshold. So in this case, we can write a force threshold or the energy threshold for the system to like to calculate the 0 quantities actually. There are some other parameters, just like the prefix, like what calculations are we doing, or like where should we write our files, or like where are pseudo potentials, something like that. And there's also like some other things which are really important in the topic. It's first the occupation factor, and in this case it shows smearing. So this means that like we have our atom, and the atom consists of an ion and the valence electrons, and smearing means like how we are putting the valence electrons in the system. The smearing method works very well in the metals because metal atoms are just all over the place and they just want to do interactions. And also we are choosing our smearing. So how we want to smear these electrons to the orbitals. So in this case, our choice is Fermi-Dirac distribution. So since we are dealing with electrons and the electrons are Fermion, it's a good approximation to do. But like if the number of the electrons in the system gets much higher or much lower, then we can, or if the material is something like a semiconductor or an insulator, we might need to choose other smearing method too. So there are other parameters. That's like there's a mixing mode. Mixing mode is actually after each SCF cycle, the system mixes the previous charge density with the next one. So it is just a local, means that we are mixing the charge density waves locally at each point instead of like the globally holding manifolds. So this is like the more precise approach because we have more weight in this case. The other things are the atomic positions. Atomic positions are just the fractional coordinates. You can like think it as the minimum is 0 and maximum is 1. So if this is like 0, 0.5, it means like it is on the corners for X and Y dimensions, but it's in the middle for the Z direction. And the selenium atoms are placed in a simpler manner. And there are other things like this is cell parameter. Cell parameter is Armstrong. So this is like size of our unit cell. Unit cell is in the size of 2.48 Armstrong. This is actually a parallelogram. So these two, there's a 120 degree between these two edges. And there's also like a 13 Armstrong value in the Z direction. So this means that we are dealing with a single material, like we are dealing with a monolayer material. It's sort of like there is something above or beneath the material is in the center, and there's nothing above it or below it. So this is in the vacuum. This put the object in the vacuum so we can get rid of any kind of interaction that we don't want to. So I mentioned the pseudo potentials. So the pseudo potential like depends on the FEF different things actually. So if I want to give some examples, so first the exchange potential. So in the the potential of the density function, we mentioned that the exchange potential. So this can be local density approximation or GJ approximation. So there are like a lot of different approximation, and each software packages like support some of them, but the others don't. So like there are many different approaches, but the GJ is like the most used one right now. LDA is just a linear approximation, so it's like a bit earlier approach rather than the GGA. There's also we can add the electron correlations in the system. So I said like that the system has weak correlations, but if we want to increase the effect of the correlations in the system, we can just write a Hubbard model for the exchange parameters. And if we choose a higher value for the exchange of electrons in the system, so we can have rather strong interactions. And we can also incorporate the Wannier interactions to the system too, and it's called DFT plus T. So in this case, we just add the usual DFT to the system plus a non-local interaction term for the layer-layer interactions in the Van der Waals case. And besides that, we can also incorporate the spin-orbit interaction to the system as well. So in this case, we deal with the non-relativistic pseudopotentials, and this non-relativistic pseudopotentials results as the non-degeneracy in the bands, and this non-degeneracy results the broken symmetries in the band structure. And in this case, we deal with more bands rather than the non-spin polarized case, actually. We can also perturb our system. So in density functional theory, we are just dealing with the Hamiltonian. So we can just linearize our Hamiltonian under the small perturbations. And this actually, this perturbation are just on the ionic position. So we just move the atoms a bit and change in the energy in the system. So by observing this change in the energy, we can construct the dynamical matrix, and also we can get the vibrational modes caused by this perturbation in the system. And like if you want to simulate the system, we can just use the phonon code for this quantum espresso. So phonon code contains like a few parameters. We mentioned the prefix parameter earlier. It's just the name of the calculation. We also file for dynamical matrix. So in the calculations, we are calculating the phonon spectrum in each Q point. Q point is just a shift of the ion from its equilibrium point in the momentum space version. Like if we shift the position of the atom and take Fourier transform of it, it just gives us our Q value with some frequencies and eigenvectors actually. So this dynamical file contains the information about these Q files. And L dispersion true is just a let us to calculate the dispersion in the system and translation symmetry correct in the system. So there's also one thing called dvSCF. It actually takes the derivative of the self-constant function potential. So this derivative actually gives us a, like if we change a position of an atom, then our potential changes, and this derivative gives of the change of that potential. And this is very useful for the interactions in the electron phonon case. So we need our Q grid. Q grid means that like how many, so in the crystal systems, we have our primitive cell. Primitive cells is just the most basic structure of the lattice. And we just multiply the structure over and over. We get our periodic structure. In this case, this 12 is just a periodic structure parameter. So it means that we are putting the same lattice 12 times in the X direction and 12 times in the Y direction. So we are making a supercell to make a, since we are making a structure more periodic, so we can calculate more Q points because it's just a Fourier transform of it. So this will actually increase the precision in the calculations too. And we also have a threshold parameter. This parameter is like much smaller than the electron case. because since the electrons are much faster than the ions, according to Born-Oppenheimer approximation, the phonokinetic energy is going to be much lower. So the energy threshold is also going to be lower than the electron case. So we are doing a lot of calculations, but so these calculations are actually like taking a lot of time, and actually like I need an approach to make these calculations faster. So I wrote a software package to do it. It's called Espresso Machine. So I am just going to talk about a bit about Espresso Machine. So it's just a tool to automate quantum espresso. And in my previous slides, I showed the input files. And this input files, there are some prefix, and it's like the sigma value. This sigma value is actually kind of pseudo temperature for the system. So this value is, we can think this value as like the smearing of a Gaussian function. So if our smearing is higher, the error is going to be higher too. So we want to decrease our smearing and hence the error. But since we want to have an adiabatic approach, so we don't want to change the system very quickly, but with a small perturbation, we can change the system and observe how the system behaves under these changes. So to observe this, we need to do like the same calculations over and over again. And in this case, I just wrote a script to do it, like automatize it. In this case, I am running an iteration over the sigma values. The sigma values are just my convergence parameters. And first, I'm doing a crystal relaxation for a system. The crystal relaxation, like I've mentioned before, that the forces in the system. So the crystal relaxation reduces the forces by changing lattice parameters. So if like there's an interaction between two atoms, or if like there's a non-zero net force in a system between atoms, and if we increase the distance between atoms, if this force reduces, then we reduce the force distance between the atoms. And this like this just changing the crystal parameters, like we are changing the shape of the actual crystal. And after we are happy with our structure, then we can start changing the position of our atoms in the system. If you like some experimental value or other thing, or like if you just want to perturb the atoms, or if you just want to shift atoms to see like how it's going to change the overall system, we just make an atom relaxation, and it helps us to find the ground state minimum energy of the atoms for like each individual atoms. And then we can run the self-constant field calculation. So this input files actually like take some parameters to run them. And for example, like there's like on the right, we can select the inputs in the actually inputs of the input file. So I just automatize the input file, and instead of like dealing with the text file, you can just put a JSON parameter to give all these values in just a single line. So this is just a very good way to put something in a very visible picture. And also, yeah, so after this calculation is done, I am also done the phonon calculations. So this is the result. So I actually find what I want. So if I need to like briefly mention this plot. So we have a system, and in the system we have a parameter. It's called the smearing parameter of the electrons. So we can think it like as analog to temperature. If we have a high temperature, like in the first figure, and if we lower our temperature, the system is going to tend to a different ground state. In this case, this is called the charge density wave state of the system. So the phonon frequency hits zero at a certain point. So this means that the phonons are locked. So it means that the atoms are not moving. So like the system are just frozen in this case. The frozen system means there's a phase change, and the phase change can be seen further on the third figure. If we go below a lower temperature, the system changes its phase, and we get negative frequency of phonons. So the negative frequency of phonons means that there's an instability in the ground state. So we need to change our ground state. So this automatization actually help us to find the instabilities of the system and like find some novel phenomena without even doing experiments. So actually, like, this simulation gives us experimental results even without doing the experiments. So when we have this result, we can, like, even though we have a hint from a material that can be like a superconductor or chargeless wave material, and like we can simulate the material before doing the experiments in the, like, the light of the similar materials, then we can let the experimenters know about this material and they can just synthesize it and make experiments on it. So this allows us to, like, save a lot of time by just doing random experiments, actually. So I mentioned, like, the electrons, ions, atoms, but we also need some orbitals in this case. So, or like at least the spherical waves, because a little bit of analytical approach would make our calculations much simpler. So in this case, we are using the Wannier functions. Wannier functions actually like a localized function basis in the density functional approach. We are just our density functionals, and we have wave functional depends on the density functionals, which are periodic, like they are block functionals. The DFT functionals are block functionals, but these are in the plane wave basis, so we don't even like much of analytic understanding in this function. So we need something more understandable, like the orbital functions. So in this case, we just make a unitary transform between two bases and then take a transform of it to get our Wannier function. So what this first equation does is actually, if we're going to start with like the inside of the parentheses, we have our density function, wave functions. Then if we apply unitary transform to this function, we get this function at different bases. And this basis, instead of the standing wave, we have orbital waves by doing this UK transformation. After this, doing this transformation, we get a Fourier transform in the momentum space to find our orbitals in the real space. So this W and R functions are actually the positions of the atoms and the values and the smearings of each orbital atom. Like if you have hydrogen and if you have s orbital, this V and R gives us the position of this s orbital in the real space, basically. And this orbitals, like doing this transformation, not everything goes as we expected. So these are not like one-to-one or unique. They are one-to-one, but they are not unique transformations. Since unitary matrices are not unique, we cannot transform them directly. So we have some errors in this transformation case, and it's also numerical calculations. So our aim is to just reduce the spreading of this Wannier functions in the real space basis, because we want our functions localized. So if they are spreads, they are not something like as you wanted. So there's also one more thing about the Wannier function, is the disentanglement of the bands. So let's say we have 20 DFT bands, like we have 20 constant states in the quantum espresso calculations. And if you want to do a calculations for a specific material, and we have like 10 orbitals in this material case, like if we need to go from 20 band space to 10 band space, we need to do some disentanglement. So in this case, this U disentanglements represent this reduced number of bands. So this unitary transform is not actually a square matrix. It's just a rectangular matrix, but its multiplication with its adjoint gives the identity element. So by using this Wannier approach, we produce a lot of data, and we need to like visualize and analyze this data. So I wrote another software package called TypePy. And so what does it do? So first I import the library. I'm very used to using Jupyter Lab. So I use it as a notebook in my calculations. First, I import the tight binding library, and I give a location for my output files. So in this case, this is like a specific path for the material. So what this software package needs, it needs a few input variables. First of them, the file path for the given simulation, and the other is the path for the or name for the non-self-constant field calculations. These NSCF calculations are a bit different from the SCF calculations. After we are done with the SCF, we just calculate the energies at individual points with a more precision. So this gives us this NSCF values. And we also have our Wannier picture. Wannier picture is just a Hamiltonian in the real space. It's just an orbital Hamiltonian. By using these two outputs from Wannier 90 and quantum espresso softwares, we can generate our tight binding model. So by using this model, we can calculate a few quantities. First of them is the energy spectrum or dispersion spectrum of the electronic structure. So in this case, I'm calculating electronic structure in a specific path. It's just the gamma MK gamma path. This is actually a special point in a lattice. So M indicates the midpoint between the corners of a hexagon, and K point is the corner of the hexagon. So this is a hexagonal structure, and gamma point is the center of the hexagon. So in this path, I am taking 1,000 points to calculate the energy, and then I just run some calculations. It's called the parallel solver function to calculate the span structure parallelly. So there's one thing about these calculations. They are very time-consuming calculations, and we need supercomputers to do them, and we need to solve them parallelly to save some time, actually. This is like one of the main aspects of my research too. And by using this TypeI, we can also like automatize it a bit further. So this is like the script version of it. Instead of notebook, I can make it like a compact version of it. So there are like a few more parameters to calculate for me. In my research, I'm calculating the linear susceptibility with respect to the change in the Fermi energy. So in this case, I need to give a temperature to calculate the Fermi-Dirac function. So my temperature is 1 Kelvin in this case. And since we are dealing with a metal, so we need to give the metallic band index for the Fermi level. So in this case, like this is just a number of my specific orbital. And Q points are indicates the, so we are taking a Q average. We are taking an average over beryllium zone with respect to some interaction weight vector. So these Q represent the interactions, and we are splitting the interactions to like a 2,000 distinct points with sampled with 1,000 by 1,000. These are like just some arbitrary numbers in this case, but to have a like a precise mesh or to have a like a good result, we need to increase these numbers so we can calculate the quantity in different points and we can like have a better results. So in this case, I am shifting my Fermi level between minus 0.2 EV to 0.2 EV, this electron volt in this case. And the materials energy level, energy bandwidth is actually like around 1 electron volt. So this is actually quite nice value. I indicate my position of my files. Then I just run the calculations to get the structure. This left one is actually for the band structure, but I actually incorporate the Fermi function too. So this chi function is actually takes a value of Q and Fermi energy. So this F means the difference between Fermi energy of the K point and the Fermi energy of psi point K plus Q point. So we are just basically measuring the difference of the 2 points, and we're actually like we are trying to answer the question of, are there any 2 point pairs which are correct to each other? So in this case, these correlations are expected to much higher in the 2/3 of gamma points because of special structure in the phonon spectrum. And we can also change the Fermi energy of the system to calculate this susceptibility in the different levels. So this actually, if you think about the experiment, this means the if we apply a potential gate to a system, we can change the energy level. So the change in the energy level is actually change the properties of the system. So we are trying to find if there's a strange behavior if we change this energy or the potential in the system. So this is actually most of my research. I'm working on these topics mainly, and these are actually quite fine and exciting topics. And this is actually the end of my talk. And by using this results in my calculations, I'm also working on an NFT collection. So I am making a lot of colorful calculations, and these things can be turned into art and share with people. And yeah, that's all from me actually. Thank you.
Let's thank Susy for this interesting talk. And we can have questions and comments from the audience. You can raise your hand or just ask.
I can ask a question.
Okay.
So Susy, thanks for the talk. I have this question. I mean, obviously, I do not understand these calculations and packages very well. And given that I come from a physics background, I am tempted to ask you. Also, I don't know the density functional theory as well. So I'm tempted to ask this question. Suppose I give you an experimental data from the literature, and it studies some properties of some molecular configurations, and apparently your packages or the ones that you're working with can calculate lots of things. What are the validity, or can you reproduce all of these results? First of all, that is my question. Secondly, you make lots of assumptions which make sense from a computational point of view. And how far can you stretch these assumptions? For instance, you gave us the simplest example of a hydrogen molecule, and they were 1 angstrom apart or something like that, those two atoms. Can you put both of the atoms at the same point on top of each other? I don't think it should be possible. So how far can you stretch this computational way?
So actually, this software gives us a playground to play with. It's just a sandbox. So you have two atoms, and you can put them in anywhere in the lattice. But probably if you put them just on top of each other, program is just going to give an error. But if you just make them a bit distant, instead of 1 angstrom, you just put a 0.01 angstrom, then you can calculate values for this context. You can calculate the force, you can calculate the energy and other things. And also if you just want to make this, if you put these two atoms closer than their original bond distance, so you're gonna increase your energy. So this energy is not the ground state energy, and hence the system wants to go to ground state. So this is the relaxation point of the lattice. And yeah, you mentioned there are some assumptions for the system. So we're actually trying to reduce these assumptions by adding some higher order correlation terms or higher order exchange terms to the system. In this case, this depends very much on the system that we are dealing with. If we are having a metal, then it means we have conduction electrons, so we can move things, and we need a different pseudo potential. Or if we have an insulator, then we cannot move the electrons, so the pseudo potential can be different. And if we have semiconductors, there should be a gap, and are we calculating the gap correctly in this case? And to answer these questions, we use different kind of pseudo potentials. So by using you need to first consider that the system that you are dealing with, then you choose those pseudo potentials. In my case, I'm working on the niobium diselenide system, and this we can put any kind of pseudo potential for niobium and selenium. But if you want to incorporate the spin orbit interactions for the system, I need to change the niobium pseudo potential with the non-relativistic one to have this non-relativistic interactions, and I can add the spin orbit interaction. So if you have some interaction or some strange behavior that's in the literature, you can find maybe pseudo potential. But if you want to go some more a fictional side and make your own strange interactions, you can maybe code your own pseudo potential. But if you want to be in the literature and mesh with the experiments, the results are actually like lower than 100% error, maybe compared to like the experiments with the calculations. I think if like it's answered this question.
Yes, yes, thank you. I mean, it was very detailed. So if just to repeat that I understood correctly, so it agrees with, I mean, you can match it to be agreeing with experimental data by
like
choosing correct pseudo potentials and so on and so forth. Okay,
and the
thank you.
parameters. And it can be like lower than 100% error.
Okay,
Or
thank you.
100% error.
Are there any questions? Okay, then I will stop recording and we will continue with our next talk in 7 minutes.